So this video is to summarize our overall rules for nomenclature, or how to name our compounds. What we'll see within chemistry is that it really is separated into two categories. We have inorganic chemistry and we have organic chemistry. We don't have to worry about the organic chemistry for this class, so we'll just kind of ignore that column. General chemistry is kind of split into the types of bonds that our compounds can have. Be they ionic compounds or bonds, ionic bonds or covalent bonds. Once we've got that category, we can further subcategorize the ionic bonds into binary and ternary. Binary just means two, and ternary means really at least three, but more than two. Right? And that more than 2 and 2 is in reference to the number of atoms present within the molecule. So if we took a look at, say, something simple that we've seen already, sodium chloride, that has 2 atoms in it, so it's a binary compound. So we would name it according to the binary system. The ternary compounds would be, say, this guy. This one is ternary because there's at least 3 different types of atoms in it. So our binary and ternary really just refer to the number of elements present. If there's 2 elements present, it's binary. If there's more than 2 elements present, it's ternary. It does not make reference to the total number of atoms present. For instance, if we switch to this compound, there are 3 atoms present, but only 2 elements. If there's 2 elements, it's named according to the binary system. Okay. And we'll see more examples as we go. The last category that we'll talk about are acids, which is kind of a weird one. It really falls under all binary, ternary, and covalent compounds. It's really just taking a compound and dissolving it in water. If it has a very particular chemistry associated with it, we give it the acid name. So, our ionic bonds. In general, all of our rules are really coming from the system called IUPAC, which you can either learn to love or hate. It's the International Union of Pure and Applied Chemistry. They've set the rules. They sat down and said this is how you name it, which is one of the tricky things. You have to name it the way they name it. If you come up with a different name, you're wrong, regardless of if somebody can draw the structure from that name. It's got to follow the IUPAC rules. So within the ionic bonds are a metal and a nonmetal. What ends up happening within ionic compounds is that you get a lot of repetition of this metal and nonmetal. Okay? That smallest repeating unit is known as a formula unit. And it can get subcategorized into our binary and our ternaries. So our binary was 2 different elements. Again, just to make sure you've got it, 2 different elements. Not saying how many, just of each of those elements. We're just saying that there's 2 different ones. And then ternary is more than 2. Typically 3, but we can get more than 3 different types. More than 2 elements. Different. Kind of makes sense. So one of the things that you'll see pop up is this word formula unit. That's really just a trigger that you're looking at an ionic compound. Because ionic compounds alternate, have a very repetitive structure, you'll notice that we've got a blue ball and a green ball. That uber repetition makes it difficult to name the entire structure, so we just name the smallest piece of it. When we look at an ionic compound, it's really composed of 2 components. One species is referred to as the cation. Most of our cations are monoatomic. There are a few exceptions to that, and we'll see those later on. So the cation merely just means that we're looking at a positive charge. That's it. Okay? And it typically applies to just metals. Someone may ask, well, why? Well, as we may have gotten to in the lecture, all of our metals carry a positive charge. And one of the reasons is they're just trying to look like our noble gases. To do that, the easiest way is for them to lose electrons from their orbitals. If they get rid of those electrons, their now net charge is positive. So nearly all of our metals will be positively charged, okay, particularly when we put them into a compound. There are some exceptions, but very, very rare. The nomenclature for our metals, or our metal cations, is actually relatively simple. It's named for the parent name of our atom, and then it's followed by the word ion. So if we take a look at some examples here, Na plus and Mg2 plus, or Mg plus 2, are named for their parent. So the symbol for Na means sodium. So there's our parent name, followed by the word ion. Really simple. Okay? Magnesium, again, same deal, magnesium and ion. One of the things that you might know is you go, well, what if I don't know the symbol name? Well, this is why we told you to memorize 30 to 50 elements. If you've got them memorized, you know what the symbol name is, and we don't have to worry about that. So you do still have to go back and make sure you've got all those elements memorized for pretty much the rest of the semester, if not the rest of your chemistry career. And there are some exceptions to that rule. Okay? Some metals, or most metals that you're going to see this semester, have the same charge. So every time we look at a sodium ion, it's going to be a +1, and we know that charge in the upper right hand corner. If we look at a magnesium ion, it's always +2, always in that upper right hand corner. If we look at a zinc ion, zinc will always be +2. So there's no need to specify the charge, because it's something that is inherent to that atom. It is always that charge. And for you to know that it's always that charge, yes, you will have to memorize that. And again, we'll get to that in just a second too. But what if there's multiple charges? For instance, if we take a look at copper, if we go through and try and name each of these two compounds below, we would have, I can spell copper ion, and the other one would be copper ion, at least according to the rules we've come up with so far. Well, those have different charges. If they've got different charges, they've got different chemistries, which means when we put them into a compound, we're going to put them into the compound in a different amount. So this is going to be kind of important. We need some way that when we say the name implies the charge. It gives us some information about it. So we do add one more piece of information when we're looking at metals that have multiple charges. Okay? That extra piece of information is really straightforward. We just want to make sure that we know that the charge for that first one is just a +1. So we'll write a Roman numeral 1 right after copper. So the Roman numeral tells us the charge on the metal. What about the copper +2? Well, if we want to specify its charge, we'll again use Roman numerals. It is now copper 2 ion. So we use our Roman numerals to specify charges. Roman numerals equal our charge. With this, it is really only our positive charge that we can use. If we end up having multiple negative charges, we'll address that in a second, because that's the next piece of this. So really our Roman numerals are key for coming up with our cations. So relatively straightforward. There is an alternative method to going through and specifying the charge. I'm not a fan of it. I don't ever remember it, but in case you want to see it, or in case you do accidentally see it somewhere down the road, there's also a Latin system for the charges on metals. That's this little section here. The lower the charge, we change the ending of the name, okay, so the suffix, to OUS. The higher the charge, we change the ending of the name to IC. some of our names started with a Latin root, so it makes sense to use those. Some of them didn't, so it's a little bit more confusing. So if we take a look at copper plus 1, it's the lower of the charge. It's referred to as, I'm not even sure I'm spelling that right, cuprous. In the case of copper plus 2, it's cupric. So if you see this us or ic ending in it in reference to a metal, it's specifying something about the charge. Okay, I know that's obnoxious. You don't see it all that often, so don't stress too much about it, but remember it in the back of your head. If you see that, think back to this slide and pull it up and see what it's supposed to be. The other part of our ions of our ionic compounds is that we have the anionic portion, or the negative portion. Okay. So our anions, when they're monoatomic, will typically apply to our nonmetals, okay, which again goes back to our electron configurations that in theory we've gotten to in the textbook. That's in reference to their willingness to accept electrons to look like the electron configuration of the noble gases. So they typically carry a negative charge. Because we've already used the really simple version of our nomenclature on the cation, we have to make it slightly more complex so that we don't get our anions and cations confused. That extra little addition is that instead of taking just the name, what we'll do is take the root name of our element and we'll change the suffix on it to an IDE ending. So if we go through and take a look, oh, that was nice, at some of these, our anion in that first case, our element is bromine. Okay, well, what we want to do is keep the root. The root in this case ends up being the brome part, and we'll follow it by IDE. So we end up with the bromide. And then we'll say ion, just to make extra sure that we know we're talking about the ion at this point. Okay? Because we've changed the suffix, typically people don't add the ion phrase to it. So if you go through and take a look at the rest of those, some of them are a little more sensical than others. Some of them don't make perfect sense. Like nitrogen, the root that we end up keeping is just the nitr, or the niter, and then we change it to the ide. Okay? So be aware that sometimes the roots aren't super obvious. It takes a little bit of practice to pick those up. Okay? One of the nice things you'll notice is that we will never ever have to specify the charge on the anion. There's a couple reasons for that. The primary reason is that in an ionic compound, all of our anions will hold the same charge. So if I look at a nitrogen bound to a metal, that nitrogen will always carry a -3 charge. That means that we then have to memorize the charge on these, and we'll talk about that too. So, when we go through to put together our name for an ionic compound, what we're going to do is combine the cation and the anion. So the basic structure of our ionic compound is taking a positively charged species and a negatively charged species, and we put them near each other. Okay? One nice question to think about on why we put them near each other is what we are trying to do is cancel those charges. Charge is inherently bad. So if you stick your finger in an electrical outlet, don't, first off. That's a bad idea. But if you did, you get a really nasty shock and be very, very unhappy with your decision to have done that. Okay? And that's because what's coming out of the electrical outlet? Well, electricity. Well, what makes electricity? Electrons. Are electrons charged? Yeah. What was that charge? -1. Good job. So, charge is bad. We want to neutralize charge. So when we look at making our compounds, compounds are made in such a way to neutralize that charge. So the overall charge for our new compound is 0. Okay, we'll keep coming back to that. So if we now look at the overall charge for our molecule, while our cation may have been positive and our anion negative, the overall compound has a 0 overall charge, and we would see that in the upper right-hand corner. So look to that upper right-hand corner and make sure that it's 0. If you came up with a name, you'll have to address the amount of cation and anion such that that charge comes out at 0. For every other, if you're given a formula trying to come up with a name, the charge is assumed to be 0 in the structure drawn. Okay, so assume that somebody put it together appropriately. When we go through and address the name, the cation, or the cationic species, all we're going to do is drop the word ion, because we didn't change anything else about the name, so we just leave the name the same. For the anion, that's our nonmetal, what we will do is we just won't change anything with the name except drop the ion again. So a quick example, which everybody already probably knows. If we look at our formula here, our cation is given first, our anion is given second. Our cation is sodium ion, and our anion is chlorine. I can spell, let me try that again. Is chlorine, but because it's in a compound, we know it's an ion, so we get rid of the ending and turn it into chloride. We can then go through and fix our name by erasing the ion, and now we sandwich everything together and we end up with sodium chloride. Relatively straightforward. What happens if you come across one of those metals where it has a charge? Okay. Well, when we go through and draw out our formula, we'll have to, or come up with our name, we'll have to make sure that that Roman numeral shows up. Okay? And then this next thing that we're really kind of getting at within this slide at least, is that again, when you look at our formula, upper right hand corner, there's nothing written. That nothing written means that the overall charge is 0. So let's check our work on this and make sure that this formula actually makes sense. Well, the charge on sodium is a +1. The charge on chloride is a -1. So all we're doing is adding up the charge contribution from our cation and the charge contribution from our anion to equal the overall charge on our molecule. And in the case of our Gen Chem class, that always needs to be 0. So 1 plus a -1 is 0. So we've put our name together fine so far. Yes, we'll see some exceptions in a little bit. So, one of the things that we really need to make sure that we go through and do is that we know what charges show up on our metals, okay, or on our ions. If we don't know the charges, it's very difficult to go through and process this. So your textbook provided a nice little slide with all of these common things on it. You'll notice that I've put some red slashes through some of these, and that's because for some reason the textbook is listing common metal ions for things that are variable, okay? Which means if it changes, and if it changes, you don't know what it's changing to, so it needs to be specified. We can't just say, oh, what's the charge for chromium? Because it's not just +3 all the time. Sometimes it's +6. Okay, so it's a pointless thing to go through and memorize. So the ones without the slash absolutely must memorize. One of the things that you'll find when we go through and do our discussion on electron configurations is that everything in row 1 will carry a +1 charge. Everything in row 2 will carry a +2 charge. We'll skip the transition metals. So these are our transition metals as far as patterns go. If we take a look at row 15, everything in row 15 carries a -3 charge. Everything in row 16 carries a -2. Row 17, a -1. The idea is what row 18 is? 0, which is why it's not on the list, because if it's got 0 charge, there's nothing to neutralize, we don't make a compound out of it. Okay. The ones that I would say are trickier to memorize would be your aluminum your zinc, your cadmium, and your silver. Okay? So those ones you absolutely must memorize. You can kind of derive their charge when we understand a little bit more about electron configurations, but it's kind of tricky in some cases. So I would focus on memorizing those four first, and hope that when we get to the electron configurations, you've got an extra little bit of material to help you memorize the rest of them. Okay? So, when going through and practicing your nomenclature, you should have this chart out in front of you so that you can go through and not have them immediately memorized. So use this chart to help you. So let's take a look at some naming practice. So let's first go through and clear everything. So some naming practice. We've already seen sodium chloride, so let's just ignore that for the moment. That was a bad example. And let's take a look at the next one. Our metal always comes first. So there's our Cu for our copper. And because it's a cation, we just write it out as copper ion. We then go through and look at our next element. Our next element is bromine. Okay. Within bromine, because it's in a compound, what we'll do is change the ending of our name to IDE to imply that it is in a compound. And we could end up with this copper ion and bromide. If we put it together, we'd end up with copper bromide. But we've got an issue. Is copper one of the ones that you should have the charge memorized on? Well, if we look above, we'll have a hard time finding copper, and that's because it's not on our list. That means that copper ion, we must specify the charge in the name. So we've got to go back to this and say, well, which copper do we have? And that gets a little bit trickier. So how can we make that decision? Well, remember that I said our cation charge plus our anion charge must equal 0. So let's set up a little equation here. We'll say I've got one copper ion times its charge, well, I don't know what it is, plus 2 bromide ions. That 2 is coming from our formula. Okay, that formula says there's 2 of them. And I know bromide carries a -1 charge. How do I know bromide carries a -1 charge? Look to our table. There it is. Bromide carries a -1. This must equal 0. Okay? And we know it equals 0 because in the upper right-hand corner of our formula, there's nothing written. Okay? So if we go through and solve this equation, what we end up seeing is x minus 2 equals 0. X must equal plus 2. Well, what did I say x was? X was the charge on the copper, okay, on our copper ion. So that means when we go back to the name for our cation, it has to be copper Roman numeral 2 ion. Okay. Now all together, I want to go through and drop the word ion because I'm saying that copper is part of the compound, and my name becomes copper 2 bromide. The 2 will specify the charge on the copper. It does not specify the amount. Okay? Let's take a look at a couple more. In this case, we're going to go from the formula, from the name to the formula. So, let's again go through magnesium. So what we could do is come up with our symbol, Mg. Oxide is our root being ox for oxygen. Okay, we now want an idea on, let's color code those, an idea of their charges. So I go up to my table, my periodic table. Magnesium is a +2 charge, and oxide, where is it, is a -2 charge. Okay, so if we go back to that formula that we were using, okay, X number of magnesium, so some number of magnesium, I don't know how many I need yet, I'm trying to do the color coding, times its charge, which is +2, plus some unknown amount of oxygens times its charge must equal, well, now I don't have the formula to look at the charge. Well, remember, all of the formulas we're giving you are 0. Okay? Unless we tell you otherwise, you must assume it's a 0 charge. Well, how do we solve this? We've got x and y, 2 variables, 1 equation. Well, really the way we're going to solve it is just by guessing. Okay? Or being really good at substituting our numbers in. If x was 0, then we don't have any magnesiums. That doesn't make sense. So we'll start with 1. We're going to use our lowest whole numbers possible. That means we would have a plus 2 plus y times negative 2 has to equal 0. Solve for y, and what do we end up with? Y equals 1. Oh, there we go. So that means when I put my compound together, I'm going to take 1 magnesium and 1 oxygen. I don't need to specify numbers underneath each of those because it's implied. Okay? If I'm going to write out the symbol magnesium, I'm saying that there is 1 magnesium there. Okay? So there's our formula. The next tricky one, I would just say it is tricky. Take a look at our iron 3. So it's Fe. Oh, but Fe we don't know the charge on. Ah, yes we do. Our Roman numeral tells us the charge is plus 3. Our sulfide, okay, again our root is the sulf, is S. We go back to our table, notice where our sulfur is. It's directly under oxygen. It has a negative 2 charge. Okay. Putting this together gets a little bit trickier. So we go back to that same idea with our formula. I have X irons, because I don't know how many there are. Its charge is plus 3, plus Y, I don't know how many oxygens there are. Man, can't color code to save my life. Times its charge of negative 2, and I meant sulfides. This has to equal our overall charge of 0. So we could go through that same process again, substituting in a number and seeing what happens. So we could say x was 1, we get plus 3, plus y times negative 2 equals 0. If we went through to try and solve this, we'd say y is equal to 2/3, or a positive 2/3. We can't have fractional charges. We have to have whole number charges. So that means x does not equal 1. So we erase it, we try it again. X is now 2 times our plus 3 plus y times negative 2 equals our overall charge of 0. We get 6 plus y times negative 2 equals 0. We'd end up going through and solving, and we'd say y equals plus 3. Cool, we just figured it out. X is 2 and y is 3. Well, what did x equal? X was the number of iron atoms. So when I go to write out my formula, I'm going to put my Fe and my S down. There were 2 iron atoms, so my 2 goes right after the iron and is a subscript. And for our sulfur, there were 3 sulfur atoms. I now have my formula for iron, what was it, iron 3 sulfide. Notice again that the 3 does not specify the amount, it specifies the charge. But because it gives us some information, we know the relationship shown in our nice little calculation here between our charge and the amount, we can calculate the amount of iron atoms present and the amount of sulfur atoms. But when we go through to write out our name, we will only specify the charge. So, nice little summary to that, our named formula. Okay, remember, this is a really, really important lesson to remember. Chemistry strives for neutrality. So pretty much everything we do in chemistry is about trying to balance charges as best we can. So when composing a formula from a name, the balance of our electrons and protons must be equal. So we have to have an overall charge of 0. And that little formula that I was working out earlier is now shown here as the number of our cations times the charge on our cations plus the number of our anions times the charge of our anions. Since our cations are always positively charged and our anions are always negatively charged, we end up looking at a difference between these two numbers, and as long as those relative charges are the same, we end up with the overall charge of 0. So when we looked at our copper bromide, okay, we come up with our name. I don't know why I'm writing it out with a CU. We've got our copper, and we have our bromide. Because copper's not on our list of things to memorize, I must specify the Roman numerals. To determine what that charge is, I have to go through and use this formula to figure out what's happening within it. Okay? And by going through and doing that, hopefully what you see is the charge on copper is 2 plus. So I specify the Roman numerals of 2. How often do you have to go through and use this formula? Okay, everybody goes, well, I could do that math in my head. That's fine. If you can do the math in your head consistently correct, don't use the formula. If you're having problems with math at any point this semester, and there's a decent portion of you that are, so don't panic, that's just the way it is, write out the formula each and every single time. Eventually you'll get used to the patterns and you won't have to write out the formula anymore, but it requires practice. Okay? Next one. Iron sulfide. Our symbol for iron is Fe. Symbol for sulfur was S. Our iron was a +3. Our sulfur's a -2. If we left this as just 1 and 1, our overall charge would not cancel out to 0. This is why when we went through and did our little calculation, we said that we needed 2 irons and 3 sulfurs. Okay? Because charge is not included in our formula, we'd have to erase those charges or rewrite our answer to be iron 2 sulfur, or sulfide. Iron 3 sulfide, sorry. So let's do one more new example, aluminum oxide. We've got aluminum, and we have oxygen. Oxygen, from our periodic table, is a -2. Aluminum is a +3. Okay? I don't know our formula for, or I don't know how many aluminums I need, and I don't know how many oxygens I need, so I will go through and solve our little formula. The number of my cation, I don't know, it's X, times the charge, +3, plus the number of my anion, times its charge, -2, must equal 0. Okay? As you go through and solve these, you may notice patterns. Have we solved this before? Yeah, we did. And when we solved it, x equaled 2 and y equaled 3. Cool. That means I can then go back through and substitute those into my equation, and I end up with the formula. Aluminum, there's 2 of them. Oxygen, there's 3 of them. Okay? There are variations off of this method. This version of it is the most consistent one for me. This is the one I'll stick with. Okay? If you want to use a different version, be aware it's a different version. Trying to get help from me might be questionable with it because I may not understand that version. So you'll have to explain to me how you're doing it first. Okay? But this method will work every single time, and it will work for a lot of other things too. Okay? So, moving on, we've got ternary ions. So if we move up to a ternary ionic compound, what we're really going to be looking at is that we've got a polyatomic ion, meaning there are many atoms, okay, in our ion. Most typically, you're looking at nonmetals bound to nonmetals, and even further, it's some nonmetal bound in a varying amount to oxygen. There are all sorts of variations or kind of pseudo-exceptions to this, but for the most part, that's the rule. what's given to you below is a nice table of the common polyatomic ions. Unfortunately, there really isn't a better method than just having these memorized. Okay, so since you don't have them memorized, you have yet another thing that you should have out in front of you when attempting to do nomenclature. You need to have the table of these common ions in front of you so that you know what they are, what their charge is, and what formula to write down for it. That is a whole lot of extra things to memorize. So what I've gone through and done is started the ones that I think are going to show up the most. Okay, so those purple ones or those stars, you need to have memorized. I guarantee I will test you on those. The other ones you may still be tested on, but you'll be tested on to a lesser extent. Okay, so if you want to pass the class, minimally, you memorize the purple stars. If you want to be in the class, you memorize a few more. If you want an A in the class, sorry, life's rough. That's why you're getting an A. Memorize them all. Okay? So, are there naming tips for dealing with these polyatomic ions? Everybody seems to come up with their own method for this. Really? No. Memorize them. That's it. Okay? Nice and simple. That's your naming tip. If you want to figure out what the charge is or what the formula is, memorize it. Don't worry about any extra kind of weird tips and all that, because your brain's going to be filled with enough other stuff. That said, there are some kind of things that you could come across. The more oxygens atom or present in your molecule, you'll typically know that the ending is an 8 ending. The less oxygen atoms present, you end up with the ite ending. So if we take a look at these two complex ions, what's going on? Well, it's sulfur with oxygen. We end up with the same charge, so I can't help you with that. You just have to memorize the charge. But the name of these is based on our root, which is our sulfur, but because there's more oxygens in our first one, it becomes sulfate. In our second one, it's still a compound with sulfur. There's less oxygen, so it's sulfite. Okay, because that was so bloody obvious. Okay, that's just the way it is. Okay, let's try another one. So I'll write up the answers to this one in 3, 2, 1. Hopefully giving you time to pause there. We go through and take a look at the nitrogen compound. 3 oxygens versus 2 oxygens. So as long as we knew that nitrogen had these two options, I could go through and say that that first one is nitrate, and that second one is nitrite. Does that really help you? I don't think so, but some people seem to like it, so I'll at least mention it. The other one to look at is if we take a look at the chlorine-oxygen complex ions. It's kind of has a pattern. What we're doing is introducing these extra terms, per-ate, ate, ite, and hypoite. So just like we did with the sulfur and oxygens, the more oxygens we've got, the 8 ending we use. However, we've got 4 possible combinations. So just switching between 8 and ite doesn't work. So if we have more than 2 options for the amount of oxygens present, or more than 2 ways to have oxygens in our molecule, we have to introduce this extra term. The per term in front or the hypo term in front. And again, if you want to remember that the per term means per and 8 means you've got 4 oxygens, by all means go ahead and do it. The more important part of this is that chlorine, running right through the middle, acts very, very similarly to bromine and iodine. So if I gave you the formula BrO3 minus, you should be able to tell me the name, because I know bromine and chlorine act similarly. So because of that, I would actually say our name is bromine, but just like I did with the chlorine, what we're doing is taking the root and we're turning it into our ending. Since there's 3 oxygens, I will go in and look at my chlorine ending, and it becomes 8. It's going to be bromate. Oh, well, that's it. Okay, well, what if I went through, changed up the formula just to be obnoxious? Let's try BRO minus. Well, again, we'll use the root of my name is the brome. Okay. With one oxygen, I have an ite ending, so it'll be bromite. But remember, I could have more, or I have more than 2 ways to combine oxygen into this, so I also need the hypo. So the name for that compound is hypobromite. So we can use reactivity patterns within some of these complex ions to predict the different nomenclatures or the different names associated with them. If that is, you find that any way confusing, I completely agree with you. I don't think it's all that helpful. I would just memorize all of them. So that's my general recommendation. You can decide with it as you will. So let's take a look at some naming practice. Again, I will go ahead and give you a time to pause right here so that you can work out these questions. And I will write up the answers in 3, 2, 1. We're going to go through these kind of fast. I'm going to underline all of my cations, and I'm going to underline all of my anions. Okay, because I know the anion shows up second. My cation for that first one is potassium. I know the symbol is K. Potassium carries a +1 charge. Bromide is Br, and it carries a -1 charge. I go through and I would take a look at 1, +1, and -1, canceling out, which then means that my formula will be just KBr. For the next one, we got lithium sulfide. So lithium is Li, it has a +1 charge. Sulfide is our sulfur with a -2 charge. I notice that those don't directly cancel out. So we'll go through and solve one long formula for this. We've got X times the charge, +1, plus Y times the charge, must equal 0. I'll assume X is 1 first, so I get +1 plus Y times -2 equals 0. I would get Y equals a half. Well, I can't have half an atom, so I go back through, erase all of my work, which you guys would never do, and we drop a 2 instead of 1 for our X, plus Y times -2 equals our overall charge of 0. We get 2 plus Y times -2 equals 0. Y equals 1. So now when I go back up to my formula, we've got our X's and Y's. Lithium was my X, and I said that was 2, so it's lithium, 2 for our subscript, sulfur, or sulfide. There we go. There's my formula. Because both of those, the lithium is one that I'm required to memorize the charge on, I don't have to worry about specifying any charges. Next one, magnesium, I know carries a +2 charge. The sulfate, notice that that's an 8 ending, so I'm not referring to just sulfur, I'm referring to sulfur with oxygen. Okay? If you have any trouble knowing which what the charges are or the formulas are for any of these, you need to go back and use the periodic table. Again, I go through and see that I don't need to balance out my charges. They work out nicely for me. And I've got my magnesium sulfate. Note that that 4 applies only to the oxygen in front of it and nothing else. Iron 3 fluoride. So iron, Fe, it's one of those ones I don't know the charge on, but I'm told what it is. +3, fluoride is an F-. To go through and do this one, I need 3 fluorides to match my iron. So it's iron and 3 fluorides. Last one. Cobalt is a CO. It's got a +3 charge. Chlorate has a formula, if I remember this one, ClO3 minus. Again, my charges don't quite balance, so what I end up with at the end for my final answer would be cobalt ClO3, but now I need 3 chlorates. So if I just put a 3 here, well, is that ClO33? No. What that's trying to say is that I have 3 of the chlorates directly in front of it. So we may need to bring in parentheses to make sure that our subscript numbers mean what we say they mean. Okay. Hopefully you didn't have any trouble solving those. And if you got questions, you can always ask me in class. Last 3 to take a look at really quickly is coming up with the names. Potassium is one that I know the charge on, so we'd be looking at potassium. That's a complex ion, so we're looking at a ternary compound. That's going to be a chlorite, not a hypo, because I have 2 oxygens. Both of those are charges that I'm supposed to know, so I don't need to specify any charges. I'm good to roll. Next one, NH4 is ammonium. So we've got ammonium, and I need to know that charge, so I don't need to specify it, followed by sulfate. Okay. Why do I not specify this 2 that's floating in there? Because that tells me how many ammoniums there are. Well, remember, when we write out the name, we don't specify how many, we specify the charge. Since the charge is required to be memorized for both of these ions, there's no need for me to specify that charge. Last one, I get chromium. Of course, I had to throw in a curveball for me, too. Chromium, and we get nitride. Well, chromium is one of those ones that I don't know the charge on necessarily, so I'm going to have to specify it. That means I have to determine what it is. So, since I don't know the charge on chromium, but I do know the amount of chromiums, it's going to be 3. I'll go through in color code. 3 chromiums times its charge plus 2 nitrogens times its charge. Uh-oh, do I know the charge on nitrogen? Darn tootin' I do. Minus 3. Okay, off of our table. This has to equal my overall charge of 0. We'll go through and now solve. 3x minus 6 equals 0. X equals plus 2. What did I say x was? X was my charge, so I need to specify that in my name by dropping in the Roman numerals. Okay? So, those are some naming practice for ionic compounds. So we now be moving into our covalent compounds. And yes, this may feel like it's going fast. So pause it at any time, rewind, do whatever you got to do. Use the textbook to kind of review the material. Our covalent compounds are a little bit easier than our ionic compounds, at least in my opinion. They're a lot easier to put together, in my opinion. When we look at the overall structures for our covalent compounds, they don't stack as nicely as our ionic compounds. And so we don't really have formula units that we would have within the ionic compound. What we have instead are molecules. This is where cool stuff can happen. Because it's also not an ionic compound, we don't have cations and we don't have anions, which means it's very difficult to decide the order in which we place the atoms. Okay, so we don't have a cation to put first. As far as which atom goes first, if we don't have a nice rule system established, then we can't decide. So this is where IUPAC stepped in and said, this is the order that they must be organized in. If you organize outside of this order, you are wrong. Okay, so this is our overall order behind it. In general, you probably won't need to know it, because when you write out the name or the formula, that order is already given to you. Right? And when we go through and do some examples, you'll see what I mean. So, when we put together our structure, the first element in the formula will maintain its name, so no changing of the name whatsoever.
So there's not even an ion term dropped into it because it's not an ion. The second element in the formula gets the new suffix "ide," just like we did for the ionic compound. Okay, so let's take a look at some examples here. For that first one, we've got carbon and we have oxygen. So we've got carbon oxide. Okay, really simple, kind of nice. For the next one, you'll notice that I was kind of tricky here. We know that this is not a polyatomic ion because in that upper right hand corner there is no charge specified, which means what I am looking at here is chlorine. Did I do this one right? Yes, I did. Chlorine bound to oxygen, so we have chlorine oxide. Okay, this is a common kind of trick thing to throw at you, so watch out for it. We may use a similar formula to a polyatomic ion, and then in a multiple choice test, one of the answers will be the polyatomic ion name, but there is no charge, which means it can't be an ion. Last one. Uh-oh, this looks a bit interesting. We've got carbon and we have sulfur, so we've got carbon and we have sulfide, but now we run into an issue. Okay, when we looked at our ionic compounds, we never specified the amount, but that's because the charge we knew, so we could determine the amount. Well, we don't know the charge for these because they aren't ions. So how do we know that there are two sulfurs in that formula? Okay, or if we looked at our name, how would we know from our name that two sulfurs need to be there? What we'll end up doing is we will specify the amount in our name. So the name for this one is carbon disulfide. So where are those prefixes coming from? It's coming from the Greek language. So if we have just one atom, we'll refer to it as mono, two atoms, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, as shown. Okay, so let's take a look at some more complex examples. We've got another name or another formula down there for us. We've got P4S3. P stands for potassium. No, you should all be screaming at your screen. No, it doesn't. It stands for what? Phosphorus. Okay, and then our sulfur, or our S stands for sulfur. Okay, but because it's the second element, it becomes sulfide. Because we now also have amounts in our formula, we're going to have to go through and specify those. The 4 translates to tetra. That needs to show up in front of the phosphorus, so it becomes tetraphosphorus. The 3 shows up in front of our sulfur, which is our trisulfide. So the formula, or the name for this compound is tetraphosphorus trisulfide. Okay, fairly straightforward as long as we know what our Greek prefixes are. The one kind of weird exception is the one atom. You'll notice that when we did the previous page, we didn't use the prefix mono to imply one atom. And in general, we don't have to supply it. There is one kind of exception, and that is the first problem that we worked on that previous slide. This formula is typically referred to not as carbon oxide, but carbon monoxide. Okay, so we do end up using the Greek prefix. Okay. It's kind of an optional thing to use. In some cases we do use it, some cases we don't. So kind of watch out for it. It may pop up on you and it may not. Typically the monoxide shows up just in the case of carbon monoxide, and that's just because it was a super common compound or a super common formula, so it picked up that mon name. You won't have to specify it for the first atom for sure. You may have to specify it for the second atom. That's the end of covalent compounds, so that's kind of nice. We're now into our last category, our binary acids. What's happening with our binary acid is we're taking either a covalent compound or it's technically not covalent, but our previous three categories and we're adding them to water. So when we put them in water, what now ends up happening is we form this hydrogen ion and a non-metal. So when we looked at charges for hydrogen, sometimes it has a -1 charge, but most of the time it has a +1 charge, just like our metals. So when we add it to water, what it tends to do is dissociate into the H+, our hydrogen ion, and the cation. Sorry, the hydrogen is our cation, and then dissociate into our anion. So if we take a look at the compound HCl, okay, so that's what we've got written right here. The compound HCl is technically a covalent compound. Hydrogen, whoops, let me fix that again. We need an N on that. Hydrogen chloride. Okay. As soon as we add the term AQ, now it's no longer hydrogen chloride. Now instead we have to specify that it's an acid. It's taken our compound and added it to water. And that's what that AQ stands for. So one of the biggest tip-offs that you'll get for naming acids is if you see that AQ. If you got the AQ, you need to name it according to the acid nomenclature. Okay? So two ways to look at our binary or our acids. We have binary acids and of course our ternary acids. And we'll have to come up with a slightly different name for each of these. In the case of our binary acids, they're named by using the prefix hydro to imply the hydrogen's presence. Okay? So you have to specify the hydro in a binary acid. We'll then follow that with the root name of the next element, and we'll change the suffix to the ic acid. So in the case of the HCl AQ, our name is hydrochloric acid, which you probably already knew. If we take a look at some of the examples down below, right? These are again binary acids because there are just two elements. We've got our hydro. Well, let's go through. Might as well color code, right? Our hydro, and then we have fluorine. So we're looking at fluor, and we change its ending to ic acid. So our name for that formula is hydrofluoric acid. For the next one, okay, maybe a little bit harder. We've got the AQ and we have the acid in front, so we know we're going for a binary acid. Hydro, we've got sulfur, so our root is sulf, or sulfur, and our ending becomes ic acid. Okay, as a quick question that you might have asked is, why is this binary? I see three elements there. Remember, our binary specifies how many elements are present, not the number of atoms. So a binary acid just means there's two different types of elements, and regardless of the amount of each of those elements. Our ternary acids mean that we have more than two types of elements. So that's our naming system. Hydro, the root name followed by our ic acid. What happens when we move up to our ternary acids? Well, of course, it's a similar situation, except now we have to come up with some way to specify slightly differently. Oh no, I didn't give you the answers. So what we're looking at is hydrogen and one of the polyatomic ions. Okay, so we've got 4 examples to work with here. If the oxyanion ending is an 8, then we change our suffix to an ic acid. You'll notice that there is no statement about adding the hydro in front of it. Remember, acid really does imply the hydrogen's presence. We didn't specify, or we had to specify the hydro in our binary acid, because if we just said the acid term, we would easily confuse that with our ternary oxyacids. Okay, so let's go through and take a look at this one again, or look at it in a new light. So we won't specify the hydro. What we're concerned about is the name of our polyatomic ion. In this case, it's perchlorate. But wait, I don't know that name. How did you know that name? I knew that name because I looked at the table. Look at those tables until you've got them memorized. If you don't have them memorized, then you would better have those tables in front of you when you're trying to solve these nomenclature questions. Okay? So that's going to be the most common advice. Because it now has the AQ and that H in front, okay, I now know that this is an acid, and what I will go through and do is erase the previous suffix and change it to ic acid. And it becomes ic acid because it said 8. Okay, our ion was perchlor 8. Looking at going in the reverse, we'll notice that we see the ic acid ending again. So that tells us a couple things right off the bat. It tells us we're going to have an H and we're going to have an AQ in our name. The next part of this is that that ic ending means that we looked at the chlorate ion. Well, the chlorate ion is Cl O3, okay, with a -1 charge. Hydrogen's a +1 charge. Those charges cancel, so my formula will be HClO3 aqueous, and we'd run those all together. What if the polyatomic ion ended with the ite ending? Okay, well, then we have to go through and come up with a new way to end our new acid name, and that's where we end up with this us acid situation. Okay, so a couple examples. We know we're looking at the acid because we have a hydrogen and an aqueous. We will not say hydro because this is a ternary acid. The name of our polyatomic ion is chlorite. Okay? Because it's chlorite, what I'll do is change the suffix to that OUS. Okay, so I get the chlorus, but because I have the H in the aqueous, it's chlorus acid. Okay? Last one, we've got hypochlorous acid. So the us means that our polyatomic ion name was hypochlorite. Hypochlorite has the formula, sorry, jumped ahead of myself there. Hypochlorite has the formula ClO minus. Because I have this acid name, I know I'm looking at an aqueous situation, and I know I have a hydrogen that has a +1 charge. Hydrogen plus and the chlorite minus, those charges cancel, so I can now just erase my charges, and I end up with my final name, or my final formula, HClO aqueous. Okay, I believe that's the last slide. Let's take one more click forward and see. Oh, quick test. So go ahead, pause the video, try and solve these 3 questions, come up with the names for them. I'll go ahead and write up the names, and then that will be the end of the video. So I'll give you that time to pause, and in 3, 2, 1. This is a nice, fun, tricky one, because what we're looking at is 3 compounds that are very drastically in their formulas, which means their names must vary as well. In that first one, you'll notice that we have no AQ, which means we're looking at a covalent compound. So to name this, we have a hydrogen. So the first name doesn't change, followed by our sulfur, which we change to IDE. There are 2 hydrogens, so it is dihydrogen sulfide. Okay. Next one, you'll notice that we have that AQ, okay, which means I'm looking at an acid, so I might write that down immediately as soon as I see that AQ. This is a binary acid. Because it's a binary acid, I know I need to start with my hydro. Okay. The next element is sulfur, so I will then specify it as sulfuric acid. So the name I've got, hydrosulfuric acid. Okay, and that's this guy. Very last one. Again, I notice the acid or the AQ, so I'll go through and specify my acid. This is a ternary acid, which means I don't want the hydro attached to it. When I put the hydro attached to this, you'll actually notice that we get the same name as we got for the previous one. So I'm going to base my name off of the sulfate ion. Because my ending ends in 8, I'm going to change it to an ic for the name. Sulfuric acid. And you'll notice that we don't get perfect root name changes. We just kind of have to deal with that as it shows up. Okay? So those would be our 3 names. 3 formulas, very similar to each other, and if we aren't careful with how we name them, we might end up with the exact same name for each of these. So that's why we've got our nomenclature to keep those separated and kind of cleaned up and away from each other.